Welcome all to chapter 4 of the e-lecture series. In this chapter 4 we'll be seeing the shaft, gears and bearing. This chapter is divided into 3 parts. In first part we'll see about the shafts, second part we'll see about the gears, and the third part we'll see about the bearings. So this session will be about the first part, which is nothing but the shafts. The transmission shaft is usually referred to a rotating machine element, circular in cross section. So it is a rotating machine element. Circular in cross section. Which supports transmission elements like gears, pulleys, sprockets, etc. and transmits power. So shafts are basically used for transmitting power from one point of the mechanism to another point. The design of a transmission shaft consists of determining the correct shaft dimension. So what is meant by design of a transmission shaft? When we say we are going to design a transmission shaft, what we basically mean is that we are going to determine the correct shaft diameter, that is estimate the shaft diameter, estimate the correct shaft diameter from the strength and rigidity consideration. So that is basically done in the design of shaft. Now the shaft is generally acted upon by 3 different types of loads. One is bending moment. Bending moment load acts on a shaft. Then we have torsional load, which acts on a shaft. Then we have axial force acting on the shaft. As we know, the bending moment causes bending stress or normal stress, gives rise to bending stress in the component. Torsional loads leads to generation of torsional shear stress. In the shaft, and the axial force leads to axial stress in the shaft. So how to design the shaft to withstand the 3 types of load? Basically the bending load, torsion load and the axial load. So first we will see about the bending load. That is, suppose we have a shaft . This is a simple example. If if M is the bending moment at any section of the shaft, then we have the bending equation, which is given by sigma by y equals M by I is equal to E by R. This is the bending equation, where sigma is the bending stress at a fiber which is at a distance of y from the neutral axis. M is the bending moment at that plane of the shaft. I is the moment of inertia of the area about the neutral axis. E is the Young's modulus of the material or the elastic modulus of the material, and R is the radius of curvature. So therefore what we get, the sigma can be written as M y by I. And for circular shaft, the moment of inertia about the neutral axis is given by pi d raised to 4 by 64. Y is equal to d by 2, which gives this as m by by 32, or we can say this is equal to 32 m by pi d cube. I will write as sigma bending is equal to 32 m by pi d cube. This is the bending stress coming in the shaft due to the load P. In this case, the maximum stress will be coming at the support section, where the bending moment will be maximum, which is given by P into L, and D is the diameter of the shaft. Now we have seen that the bending stress is given by 32 m by pi d cube. This is for a solid shaft of dia D. What about a hollow shaft? Sorry, with inner dia Di and outer dia Do. In this case, the moment of inertia is given as pi by 64 to do raised to 4 minus di raised to 4. Y is given as do by 2. In this case, I'll take do outside. So what we get is 1 minus 4, and y is equal to do by 2. If we put that di by do is equal to some parameter k, then the moment of inertia will become pi by 64 do raised to 4 1 minus k raised to 4. Y is equal to do by 2. So in this case, what will be the bending stress? Bending stress sigma will be given as my by I, that is equal to m into do by 2 divided by pi do raised to 4 by 64 into 1 minus k raised to 4. Now this can be written as sigma b is equal to 32 m by pi do cube into 1 minus k raised to 4. This is the bending stress in a hollow shaft. The m is the bending moment, maximum bending moment in the shaft, and do is the outer diameter, di is the inner diameter, and the diameter ratio k is given as di ratio of inner diameter to outer diameter. In this case, this bending stress will be given as 32 m by pi do cube into 1 minus k power 4. So this is the bending stress which comes, this is a normal stress which comes mainly due to the bending moment acting in the shaft. Now we will see about the axial stress coming in the shaft due to some axial loads. So second one is basically axial loads, which causes nothing but the axial stresses in the shaft. If F is the axial force acting on the shaft, then we have normal stress sigma is equal to F by A, where A is the area of cross section of the shaft. It is given as pi d raised to 4, pi d square by 4. So the normal stress will be given as 4F by pi d square. This is the axial stress in a solid shaft. Axial stress coming in a solid shaft of diameter d. Now what about hollow shafts with the inner diameter di and outer diameter do? In this case, the area, so for the hollow shaft of the inner diameter di and outer diameter do, the area is given as pi by 4 into do square minus di square. Therefore the axial stress is given by F by pi do square minus di square by 4. So taking this above, we get 4f by pi do square into 1 minus di by do square, where we take the do outside and the ratio di by do is given as a parameter k. So we have the maximum axial stress coming in the shaft as 4f by pi do square into 1 minus k square. This is the axial stress in a hollow shaft. Axial stress coming in a hollow shaft of dia, di and do. And in this axial stress, if the axial force is compressive, we know that when a compressive force is acting on a compressive axial force acting, there is a possibility of buckling. So we have to take some column action factor. Then we take alpha as the column action factor. When the axial force is compressive, when the axial force is tensile, this column action factor is taken as 1. So in this case, the normal stress will become 4 alpha f divided by pi do square into 1 minus k square. And for tensile stress, for tensile loading, alpha is equal to 1. So this is the axial stress coming in the shaft due to the axial force of magnitude f, where f is the magnitude of the axial force, alpha is the column action factor, which is equal to 1 for tensile load, and the value depends it will be varying for compressive load. And do is the outer diameter of the shaft, and k is the ratio of inner diameter to the outer diameter. Therefore, we have seen that if f is the axial force acting on the shaft, the axial stress is given by 4 alpha f by pi do square into 1 minus k square, where alpha is the column action factor, and f is the axial force acting on the shaft. It will be compressive here, and do is the outer dia of the shaft, and k is nothing but the ratio of the inner diameter to outer diameter. And how do you get the value of alpha? The column action factor alpha is given as 1 by 1 minus 0.0044 into L by k. For L by k less than 115, and the value of alpha will become sigma yc by pi square ne into L by k whole square for L by k greater than 115. And this value of n, and we know that since buckling is very much familiar with the main term familiar with the buckling is the slenderness ratio of the shaft, so therefore the column action factor will also depend on the slenderness ratio, which is nothing but ratio L by k. And in this above equation, the value of n is equal to 1.0 for hinged end, it's equal to 2.25 for fixed end, and 1.6 for ends partially constrained. And k is the radius of gyration, and L is the length of the shaft, and sigma yc is the the yield stress in compression. So these are different parameters coming in the above equation. Now that is about the axial stresses. Now we will see the stresses due to the torsional loads. The third one is the stresses due to torsion. For torsion loading of shaft, we know that when torsion load is acting, the stresses generated will be mostly the shear stress, and that is given by the torque, the twisting equation or twist equation, which is given by tau by r is equal to T by J is equal to C theta by L. This equation we have come across in the strength of materials, where tau, the shear stress of a fiber at a distance r from the center of a radial fiber, and r is the distance from the center, so this is J, T is the torque acting at that cross section, or at that plane what is the torque, and J is the polar moment of inertia or the second moment of inertia. Polar moment of inertia and C is the rigidity modulus of the material of the shaft. Theta is the angle of twist, and L is the length of shaft. So these are different parameters. Therefore, we can get that the shear stress caused in the shaft is given by TR by J, and for circular shaft, solid circular shaft of diode D, the polar moment of inertia is given by pi d raised to 4 by 32, and R will be given by d by 2, or it will be capital R. Therefore, maximum shear stress will be at the outermost fiber. Therefore, R is the distance of the maximum stressed fiber from the center, that will be equal to d by 2. So, substituting these values, we get tau is equal to T into d by 2 divided by pi d raised to 4 by 32. This will be given as tau is equal to 16 T by pi d cube. This is the shear stress coming in the shaft at a cross section where the torque is T and D is the diameter of the shaft. So what about hollow shaft? When we have a hollow shaft of inner diameter di and outer diameter do, we know that polar moment of inertia is given by pi by 32 into do raised to 4 by di raised to 4, and r is equal to do by 2. So taking the do outside, we get this as pi do raised to 4 by 32 into 1 minus k raised to 4. So we get tau is equal to 16 T by pi do cube into 1 minus k per 4. This will be the maximum shear stress coming in the shaft due to the torque T for a hollow shaft of inner diameter di and outer diameter do. This will be the maximum shear stress in a hollow shaft of dia di and do as the inner diameter and the outer diameter. This is the shear stress coming due to the torsional loading. Now we will see what happens when we have a combination of these loadings. Therefore, to sum up, we can say the bending stress in the shaft is given by 32 m by pi d cube for a solid shaft, or it is given as 32 m by pi do cube into 1 minus k raised to 4. This is the bending stress in the shaft. Then we have the axial stress in the shaft given as 4 f by pi d square for a solid shaft, and for the hollow shaft it is given by 4 alpha f by pi do square into 1 minus k square, where alpha is the column action factor, which is taken as 1 for tensile loading, and it is applicable only for compressive loading, just because during compression of the shaft there is a possibility of buckling to take place. If the angle of when the slenderness ratio is high, there is a chance of buckling taking place. Then finally we have seen the torsional loading, torsional stress, which is given by tau is equal to 16 t by pi d cube, or it is given as for hollow shaft it will be given as 16 t by pi do cube into 1 minus k per 4. So this is for a hollow shaft, and this is for the solid shaft. Now these are the stresses coming in the shaft due to the bending load, axial load and torsion load, each acting separately. Now what happens if we have a combination of these loads acting on the shaft, that is combined bending and axial stress. So in combined axial and bending stress mein, the bending stress is given by 32 m by pi do cube into 1 minus k raised to 4, whereas axial stress is given by 4 alpha f by pi do square into 1 minus k square, where alpha is the column action factor. Now when both the stresses are axial or normal stress, both the normal stresses are axial, then the net normal stress sigma is given as the sum of these two normal stresses, that is nothing but 32 m by pi do cube into 1 minus k raised to 4 plus 4 alpha f by pi do square into 1 minus k square. So this is the total normal stress acting on the shaft due to the axial loading as well as the bending loading. And we have seen that the maximum shear stress acting on the shaft is given by 16 t by pi do cube into 1 minus k raised to 4. This is the shear stress and this is normal stress. Then we have seen when we have a combination of normal stress and shear stress acting on a body, the maximum stress in the body is found out using the principal stress theory. So as per principal stress theory, tau max becomes equal to square root of sigma x minus sigma y by 2 whole square plus tau xy square. In our case, sigma x is equal to sigma, which is given above, sigma y is not there, and tau xy is also given as tau. So we have this maximum shear stress as square root of sigma x by 2 whole square plus tau xy square. This is the maximum shear sorry, this is the maximum shear stress coming in the shaft due to the axial loading as well as the bending loading. Therefore, substituting for the above above parameters, we get tau max equals 16t by pi do cube into 1 minus k power 4 into square root of CBM into M plus alpha f do into 1 minus 1 plus k square divided by 8 square plus Ct into t whole square. This is the maximum shear stress going to come in the shaft when it is having all the types of loading, that is bending load, and then we have the axial load, and then we have the torsional loads. And all loads are acting together on the shaft. Maximum shear stress given by this relation, where T is a torque at any section, DO is the outer diameter of the shaft, K is the ratio of inner diameter to the outer diameter, CBM is the factor modifying the bending moment, and Ct is the modifying factor for the torque to account for the dynamic effects. Alpha is the column load action or column action factor. F is the axial force acting on the shaft. DO is the outer diameter of the shaft, and K is the ratio of inner diameter to the outer diameter. So this is the maximum allowable stress in a shaft when it's having a combination of normal and shear stress. Now we'll try to solve some problems so that we can appreciate the concepts in a better way. Okay, now we'll see this problem. The outer diameter of a hollow shaft is twice its inner diameter. The ratio of torque carrying capacity of the hollow shaft to that of a solid shaft of the same material and of the same outside dia is what? So what is torque carrying capacity? So okay, what we'll write out, what are the parameters given? The outer diameter is given as 2 times inside diameter, or K is nothing but di by do is equal to 1 by 2. And what is the torque carrying capacity? We know that the shear stress is given as 16 T by pi d cube for the solid shaft, and for the hollow shaft is given as 16 T hollow by pi do cube into 1 minus k raised to 4. Now we are given that both are made of the same material. If both the materials are same, then tau s should be equal to tau h. The maximum allowed shear stress should be same in both the materials, and the outside diameter is also same, so we can say d is equal to d naught. Then what they have asked is the ratio of the torque carrying capacity of hollow shaft to that of a solid shaft. So hollow shaft will be given as tau h into pi do cube into 1 minus k raised to 4 by 16, and T solid will be given as tau s into pi d cube by 16. Therefore Th by Ts will be given as 1 minus k raised to 4. And what is k here? K in this problem is given by 1 by 2. So this will be 1 minus 1 by 2 raised to 4. That's equal to 1 minus 1 by 16. That's equal to 15 by 16. Therefore, the ratio of torque carrying capacity of a hollow shaft to a solid shaft is given by 15 by 16. So we'll take another problem. Two shafts A and B are made of the same material. The diameter of shaft B is twice that of shaft A. The ratio of power which can be transmitted by shaft A to that of the shaft B. Now it is given that both are made of the same material. That means tau A is equal to tau B, and diameter of shaft B, that is dB, is equal to twice the diameter of shaft A. Now what is the ratio of power transmitted by shaft A to the power transmitted by shaft B. What is the power transmitted by a circular shaft? It's given by 2 pi nt by 60, where T is the torque transmitted and N is the speed of rotation in RPM, rotations per minute. Therefore, we can write PA by PB is equal to TA by TB. So, what is tau A? Tau A is equal to 16 TA by pi d cube, or we can write TA is equal to tau A pi d cube divided by 16, pi dA cube divided by 16. So, the ratio of TA by TB will become tau A into pi dA cube by 16 whole divided by tau B into pi dB cube by 16. Now tau A is equal to tau B, so this gets cancelled. So finally we get this as dA by dB whole cube. And what is dA by dB? We already know that dB is equal to 2 times dA. Therefore dA by dB is equal to 1 by 2. So therefore ratio of power transmitted PA by PB will be equal to dA by dB whole cube, that's equal to 1 by 2 whole cube is equal to 1 by 8. So this way we can solve the questions easily once we know the concepts. We will discuss some more technical things here. Sorry. So we have seen that when we have a combined loading of bending and torsion, we have the bending stress is given as 32 m by pi d cube and the shear stress is given as 16 t by pi d cube. By the principal stress theory, we know that if sigma x and sigma y are the nominal stress and tau xy is the shear stress coming in a component, then the principal stress is given as sigma x plus sigma y by 2 or minus square root of sigma x minus sigma y by 2 whole square plus tau xy square. So in our case we have sigma x is equal to 32 m by pi d cube and sigma y is equal to 0 and tau xy is equal to 16 t by pi d cube. Substituting these relations, we get sigma is equal to 16 m by pi d cube plus square root of 16 m by pi d cube whole square plus 16 t by pi d cube. Now this can be written as 16 by pi d cube into m plus square root of m square plus t square. If you take sigma effective as 32 m effective by pi d cube, then we have sigma is equal to 16 m effective by pi d cube. Equating these two equations, we get the effective bending moment is equal to m plus square root of m square plus t square. Similarly, the maximum shear stress is also given by maximum shear stress will be this much term of this equation. So it will be 16 by pi d cube into square root of m square plus t square. This is equal to 16 t effective by pi d cube, or the effective torque is given as square root of m square plus t square. For combined loading, the effective bending moment is given by m plus square root of m square plus t square, and the effective torque is given as square root of m square plus t square. We'll take another problem. A shaft is subjected to a fluctuating loads for which the normal torque T and the bending moment M are 1000 Newton meter and 500 Newton meter respectively. If the combined shock and fatigue factor for bending is 1.5 and the combined shock and fatigue factor for torsion is 1.2, then the equivalent twisting moment of the shaft. So what are given? The torque is given as, the normal torque is given as 1000 Newton meter. The bending moment is given as 500 Newton meter, and the shock and fatigue factor for torsion is given as 1.2, and the shock and fatigue factor for the bending moment is given as 1.5. So what is the equivalent twisting moment? The equivalent twisting moment the equivalent twisting moment is given as T effective is equal to square root of m square plus t square. Since here dynamic effects are also to be taken, so this becomes equal to square root of Cb into m whole square plus Ct into t whole square. That will be square root of Cb is 1.5 into m is 500 whole square plus Ct is 1.2 into t is 1000 square. So that will be how much? 1.5 into 500 square plus 1.2 into 1000 square. So this is not 1.2, this is 2. So this is 2 into 1000. 1.5 into 500 square plus 2 into 1000 square is equal to square root is equal to, this becomes equal to 2136 Newton meter. Be the T equivalent or T effective. Sorry. So thus we can find out what is the equivalent twisting moment coming in the shaft. So we'll see another problem here. A solid shaft is transmitting 1 megawatt power at 240 rpm. The diameter of the shaft, if the maximum torque transmitted exceeds the mean torque by 20% and maximum allowable shear stress is 60 Newton per mm square, will be. So in this case, what is given? The power transmitted by the shaft is 1 megawatt, that is 1 into 10 power 6 watts. The RPM of the machine is 240 RPM. Then the maximum torque exceeds the mean torque by 20%, that means T max will be 1.2 times the T mean, and the allowable shear stress is given by 60 Newton per mm square. If that is the case, what is the diameter of the shaft? What is the diameter of the shaft? Okay, so from the power and the RPM we can find what is the mean torque. That will be given as 60p by 2 pi into n. That will be given as 60 into 1 into 10 power 6 divided by 2 pi into 240 RPM. This will be 60 into 1 into 10 power 6 divided by 2 pi into 240. This will be 39,788 Newton meter. Therefore, T max will be 1.2 times T mean. So this will become equal to 47,746 Newton meter. We will work in the units of Newton millimeter. So this will become 47.746 into 10 power 6 Newton millimeter. This is the maximum torque, and we know that the maximum shear stress is given by 16 T by pi d cube. Therefore, d cube is equal to 16 T by pi into tau. Therefore, what will be d cube? D cube will be 16 into 47.746 into 10 power 6 divided by pi into tau is given as 60 Newton by mm square. This will be d cube. This will be coming to how much? 16 into 47.746 into 10 power 6 divided by this will come to 405.36 into 10 power 4 millimeter cube. Therefore, d will be cube root of that. That will become 159.4 mm. That is close to 160 mm. That is the diameter of the shaft. So we will see one more problem. A shaft of 60 mm diameter is capable of transmitting 30 kilowatt power at 300 rpm. To transmit 45 kilowatt at 200 rpm, the diameter of the shaft of the same material will be what? So we are given that the shaft diameter of 60 millimeter is capable of transmitting power of 30 kilowatts at 300 rpm. Therefore, if it has to transmit 45 kilowatts at 200 rpm, what should be the diameter of the shaft? So that's the question. So for the first case, the torque transmitted will be 60 p by 2 pi n. So 60 into 30 into 10 power 3 divided by 2 pi into 300. This will be 30 into 10 power 3 divided by 2 pi into 300. So 955 Newton meter. Therefore, the maximum shear stress will be 16 T by pi d cube. Now this will be 16 into T is 955 by pi into d is 60 mm, 0.06 meters. So this into 16 divided by into 0.06 cube. This will become 22.516 to 10 power 6 Newton per meter square. Now this is the maximum allowable shear stress in the material. Now if this is the allowable shear stress in the material, to transmit 45 kilowatts at 200 rpm, what will be the diameter? So for second case, the torque transmitted will be 60 p by 2 pi n. That's equal to 60 into 45 kilowatts by 2 pi into 200. This will be 2148.6 Newton meter is a torque to be transmitted, and we know that the maximum allowable shear stress will be 22.516 into 10 power 6 Newton per meter square. So what will be the diameter? So what will be the diameter? We know that tau is equal to 16t by pi d cube, or d cube will be equal to 16t by pi tau. So we can find out d cube. It will be 16 into the new value of torque is 2148.6 divided by pi into tau is 22.516 into 10 power 6. 16 into 2148.6 divided by pi into 0.516 into 10 power 6. Cube root of answer is equal, this is equal to 4.8586 into 10 raised to minus 4 meter cube. Therefore D will be equal to 78 mm, will be close to 80 mm. So this way we can find out this way we can easily solve the problems in this chapter relating to the transmission of power, design of shafts for transmission of power. These problems can be easily solved once we know the concepts. So with that we come to the end of this first part of this chapter on shafts. Thank you.